Your brain has a secret language it only speaks when you're asleep. Strange electrical patterns that never occur during wakefulness suddenly appear, creating a neural code that scientists are still working to fully understand. This hidden communication happens during N2 sleep, the second stage of your nightly journey, and is where some of the most important work of sleep begins. As N1 sleep deepens, your consciousness finally breaks its last tenuous connections with the outside world. Your awareness of your surroundings fades completely, and you cross the threshold into true sleep. This is N2, a state where your brain operates under entirely different rules than it does when you're awake. The shift is so dramatic that if scientists showed you an EEG recording from this stage without telling you what it was, you'd never recognize it as human brain activity. What makes N2 sleep instantly recognizable on an EEG are two distinctive patterns that appear nowhere else in human experience: sleep spindles and K complexes. Sleep spindles look exactly like their name suggests, brief bursts of electrical activity that create a spindle-shaped pattern on brain recordings. These sudden accelerations in brainwaves occur when groups of neurons fire in perfect synchrony at 12 to 14 hertz for about half a second to a second and a half. Imagine ripples forming on a calm lake, briefly intensifying, then fading away. That's how sleep spindles appear on brain monitoring equipment. K-complexes are even more dramatic, sudden sharp spikes in electrical activity followed by a slow wave. On an EEG, they look like the letter K, a steep upward peak immediately followed by a downward plunge and then a final upward curve. These striking brain events last only a second or two, but represent massive, coordinated firing across large portions of your cerebral cortex. These brain patterns serve crucial functions. They act as neural bouncers, protecting your sleep by actively blocking external stimuli from reaching your consciousness. When a sound occurs in your bedroom, maybe a car driving by or your partner turning over, sleep spindles suppress the brain's response to these potential disturbances, creating a barrier between your sleeping brain and the waking world. K-complexes serve a complementary purpose. When a stimulus is potentially important, like someone calling your name, the K-complex represents your brain briefly checking the stimulus before dismissing it and maintaining sleep. Think of it as your brain momentarily opening one eye to ensure nothing important is happening before returning to sleep. During N2, your brain begins actively processing information while your awareness. This is when memory consolidation kicks into high gear. Sleep spindles play a critical role in transferring information from your hippocampus, where short-term memories are initially stored, to your neocortex, where long-term memories live. This transforms fragile new memories into more stable, permanent ones. N2 sleep dominates your night, typically accounting for about 50% of your total sleep time, more than deep sleep and REM sleep combined. Each night, your brain dedicates hours to generating these distinctive electrical patterns, suggesting they serve functions essential to your survival and cognitive health. During this seemingly quiet period, your brain is methodically sorting through the day's experiences, strengthening important neural connections while weakening irrelevant ones. This selectivity is crucial. Your brain encounters too much information each day to store everything. N2 sleep is when your brain decides what's worth keeping and what can be discarded, a process neuroscientists call synaptic pruning. Imagine your brain as a garden. During wakefulness, new connections between neurons grow abundantly, like plants sprouting everywhere. During sleep, especially N2, your brain acts as a gardener, strengthening connections that represent important information while pruning away less useful ones. This prevents your neural networks from becoming too cluttered and energy-intensive. Research has found fascinating correlations between sleep spindles and cognitive abilities. People who naturally produce more sleep spindles tend to score higher on tests of general intelligence. When researchers teach people new information and then monitor their sleep, those who generate more sleep spindles typically show better recall the next day. Sleep spindles might be particularly important for procedural memory, your ability to learn physical skills. When people learn a new motor task, like playing a musical sequence, their brains produce more sleep spindles that night, especially in the regions involved in the learned task. The more spindles they generate, the better they perform the skill the following day, suggesting these unique brain waves help program new movements into your motor cortex. The strength of emotional reactions influences which memories your brain preserves. Emotionally charged experiences generate stronger responses in the amygdala, signaling to the sleeping brain that these memories are likely important for survival. This is why emotionally significant events typically stay with us longer than mundane ones. Learning-related experiences also receive preferential treatment. Information that builds on existing knowledge or relates to current goals is more likely to be retained. Your sleeping brain essentially asks, is this information useful? And does this connect to what I already know? Memories that pass these tests are more likely to be consolidated during N2 sleep. As you sink deeper, your brain begins something even more strange. The deep descent, slow wave sleep. What happens when your brain goes into its deepest, most mysterious state? After passing through the lighter stages of sleep, you eventually sink into what scientists call slow wave sleep, or N3, the deepest form of non-REM sleep. This is the phase where your brain and body distance themselves furthest from wakefulness, entering a state profoundly different from anything you experience while conscious. The name slow wave sleep comes from the distinctive electrical activity visible on an EEG during this phase. Your brain generates powerful delta waves, large, slow oscillations that sweep across your entire cerebral cortex like rolling thunder. These waves occur at a frequency of less than 4 Hz, with brain cells firing in synchronized patterns just a few times per second, dramatically different from the rapid desynchronized activity of wakefulness. These slow waves represent massive coordination between billions of neurons, all firing together and then pausing together in a rhythmic pattern. This synchronized activity is so powerful that your entire brain essentially pulses in unison, a phenomenon entirely absent during wakefulness or lighter sleep stages. The depth of this sleep creates distinctive effects. Waking someone from slow-wave sleep triggers sleep inertia, a state of severe disorientation and confusion lasting several minutes. The person might stare blankly, respond inappropriately to questions, or show significant impairment in thinking. Their brain, deeply disconnected from the external world, struggles to reconfigure for conscious awareness. Children experience particularly intense sleep inertia because their young brains produce stronger delta waves than adults, creating even deeper sleep. Parents sometimes mistake this normal response for something serious when their deeply sleeping child temporarily cannot become fully alert. During this deepest sleep phase, critical physical restoration occurs. Growth hormone secretion peaks, stimulating tissue repair and cell regeneration. Muscles receive increased blood flow, delivering oxygen and nutrients while removing waste products. Energy stores replenish, and enzymes repair cellular damage from daily activities. Slow-wave sleep also provides your immune system a significant boost. During deep sleep, your body increases production of cytokines, proteins that fight infection, inflammation, and trauma. This explains why sleep becomes crucial when you're sick or injured. Your immune system leverages these slow-wave periods for maximum efficiency. In 2012, researchers discovered perhaps the most remarkable aspect of slow-wave sleep, the glymphatic system. This previously unknown network functions as your brain's dedicated cleaning crew. While somewhat active during wakefulness, it transforms into a full-scale maintenance operation during deep sleep. During slow-wave sleep, the space between brain cells expands by up to 60%. This expansion allows cerebrospinal fluid to flow more freely through brain tissue, essentially power washing it clean of metabolic waste. The glymphatic system operates like an overnight cleaning service, removing debris that would otherwise accumulate and potentially damage neurons. One crucial waste product this system removes is beta amyloid, a protein fragment that accumulates in Alzheimer's disease. Even one night of poor sleep leads to measurable increases in beta amyloid, while quality sleep reduces these levels. This establishes a direct connection between sleep quality and your brain's defense against neurodegenerative diseases. The glymphatic system has revolutionized our understanding of sleep's purpose. Beyond memory and emotional processing, sleep physically cleans your brain at the cellular level. Without adequate slow-wave sleep, waste accumulates between neurons, potentially contributing to cognitive decline and increasing disease risk. This cleaning process requires so much energy that it cannot efficiently occur during wakefulness. Your brain must temporarily suspend conscious activities to redirect resources to this maintenance. It resembles a restaurant closing between meal services for cleaning. Some operations simply cannot happen efficiently during normal operation. While cerebrospinal fluid washes away waste, other mechanisms simultaneously repair DNA damage in neurons, restore cellular components, and strengthen important neural connections. Together, these processes form a comprehensive maintenance system, keeping your brain healthy. Slow-wave sleep diminishes as we age. Children spend significantly more time in this deep sleep stage than adults. By our 70s, some people produce almost no delta waves. This reduction helps explain why older adults experience more fragmented sleep and face higher cognitive decline risk. Without sufficient slow-wave sleep, their brains cannot fully activate the glymphatic system's clearing function. Researchers now investigate ways to enhance slow-wave sleep in older adults, potentially preventing or slowing neurodegenerative diseases. Approaches include acoustic stimulation with specific synchronizing sounds, electrical stimulation, and medications targeting deep sleep. Most healthy adults spend about 13 to 23% of their sleep time in slow-wave sleep, with the deepest periods occurring during the first half of the night. This makes the first few hours of sleep especially important for physical restoration and brain health. Consistently cutting sleep short primarily sacrifices these crucial deep sleep periods. While delta waves dominate this phase, your brain also produces compounds that help regulate sleep depth. Adenosine, which builds up during wakefulness creating sleep pressure, peaks during slow-wave sleep before gradually clearing, ensuring your most restorative sleep happens when your body needs